Welcome back to ISOMath. Today we're going to talk about the exponential function and how to take a shortcut derivative of exponential functions. Alright, find the derivative of a shortcut derivative of an exponential function. Remember, exponential functions are something on the form of 7 raised to the x, where I have a known number raised to a variable. Or it can even be e to the x is a common one, because e, remember, is a known number. It's an irrational number, but it's a known number. So we're interested in finding the derivative of examples like this. And we're also going to talk about what if we had 7 to the 5x, or e raised to the 5x squared. So we're going to try to take care of all these in one pop. Alright, so first of all, we're going to talk about the derivatives of exponential functions. So let's talk about that first one we were talking about. So we wanted to find the derivative of 7 raised to the x. According to this rule, up here, the shortcut rule, a, in this case, my a value is going to be my 7, and obviously my x is going to be x. So it comes out to being ln of a, or in this case 7, times 7 to the x would be my derivative, and that is the case. Now I want to go over to e to the x, and you notice on this rule, e to the x, it says, hey, the derivative of e to the x is simply e to the x. But I want to show you the long way first to show you where that's derived from. We talked about before e being a known number, so this is nothing more than a to the x. It just happens to be an e value. Remember, if I use that rule over here, that would tell me that I need to take, in this case, my a value would be e. So this would be ln of e times e to the x. And believe it or not, ln of e has a value of 1, we should all be comfortable with that 1. So in reality, yes, it just simply comes out to being e to the x. But I wanted to show you the long way that ln of e is there, but it always equates to 1. So that's why the shortcut rule is e to the x. But what I really want to show you now is incorporating what we call the chain rule into some of these functions, because that's going to be coming up quick. And an example of that would be if I was asked to find the derivative of 7 to the 3x. Now what happens on this case is now I have a function up top. So this actually falls into a different category, because this is no longer just 7 raised to an x. This is going to be where my base, yes, my base a is 7, but my thing up top now is a 3x, and we're going to call that u. I'm going to call u equal to 3x. And what I need to find also is u prime, or the derivative of u. And taking the derivative of 3x, we know that to be 3. And because the rule that we're going to use is now this rule down here, and this is embedded with the chain rule. So it says if I'm trying to find the derivative of, say, in this case 7 to the 3x, it's going to be, if I'm finding the derivative, it's going to be the ln of a, and a being 7, so it's going to be ln of 7 times the function as it is, so it'd be 7 raised to the 3x, times u prime. Well, u prime happens to be 3 because we figured that out, and that's end up going to be 3 ln of 7 times 7 to the 3x, and that is my derivative utilizing the chain rule. Now I just want to show you something, because you said rather than try to go through and memorize both these rules, believe it or not, you can get through your life only knowing this rule. Why? Because let's go back to our original example. When I was trying to find the derivative back before, 7 to the x. Remember, if I use this new rule that I had, this one rule only, I can classify, obviously, my a is going to be 7, my u is going to be x, and u prime, the derivative of u prime, or derivative of x in this case, is going to be 1. So if I utilize that rule, that's going to tell me it's ln of 7 times times what it is, a to the u, times u prime, when u prime equals 1. And that gives me ln of 7 times 7 to the x. And guess what? That is what I got before. That is what I had before. So you can go through memorizing both rules. Obviously, that if it just but this rule right here only applies when it's raised to a single x, while this rule down here will apply to any function, any case. So I would recommend going through and going with that guy, so because you'll be able to get everything from that. Now let's take a look at e to the x. Now looking at e to the x, let's say we had e raised to 5x squared. I no longer can use that rule because it won't apply, because it's not raised to single x. But if I go here and say, alright, my my u value here is going to be 5x squared, and then u prime using the constant multiplier and power rule is going to end up being 10x. I can now apply this rule down here to get it. So my derivative of this guy is going to be, according to this rule, ln of e times the function as it is, which is e to the 5x squared, times u prime, and u prime in this case is 10x. And obviously this piece out there becomes 1. I can move the 10x out in front, so it leaves me with 10x times e to the 5x squared. And that is my derivative for e to the 5x squared. So again, and if I go back to my original example as well, if I had just e to the x to find out, if I use this rule, derivative of e to the x, in this case obviously my u equals x, u prime equals 1, and I utilize this rule again down here, that's going to give me ln of e times e to the x times 1, and we know that that equates out to being 1 and 1, so I am again left with e to the x. So our recommendation, rather than trying to memorize two separate rules here and here, it's better off to not even memorize these two separate rules, but actually only memorize that rule, because that is going to be, that encompasses e to the x, encompasses e to the 5x, also 7 to the x, or 7 to any 8 raised to the 5x, anything of that sort. So our recommendation is just get to know this guy inside and out, and it will cover every rule that you know, with the understanding that, hey, this a value, this a to the u, this e to the u is nothing more than a to the u, because e is a known number. It's an irrational number, but a known value. So this is the rule you want to get embedded in your memory banks, and it applies. It will work for every rule, any exponential function that exists. Let's try one all together. So here we're going to be asked to differentiate 3 to the x plus 4 to the 2x plus 5 e to the x plus e to the 7x. Using the sum and difference rule, because I'm separated by plus or minus signs, in this case all plus signs, I can evaluate them individually. So that's going to be, I can take care of 3 to the x separated by another plus sign. Is going to be, I will need to find the derivative of 4 to the 2x plus a derivative of 5e to the x plus the derivative with respect to x of e to the 7x. So here again, that's my straight up exponential rule. So when I equate that out, let me get a different color going here. When I go out with that, that's going to give me nothing more than ln of 3 times 3 to the x. No problem there. Now this guy, I'm going to use, here I have to use that chain rule, that embedded a to the u rule. And after I go through all that stuff, I'm going to end up with ln of 4 times 4 to the 2x, and then I got to take the derivative of what's up top, which is derivative of 2x with respect to x is going to be nothing more than 2, and yes, I can move that 2 out in front. And then here I'm going to have constant multiplier, so I'm going to have that 5 out in front. E to the x, when I do is, yes, I can do the long way. I'll do the long way first. It's going to be ln of e times e to the x, and we'll equate that in a second. And then here I'm going to end up with ln of e again times e to the 7x, and then I got to take the derivative of what's up top, which ends up being just 7. So after I equate this all out, so I got ln of 3 times 3 to the x, and here I'm going to move this 2 out in front, so I got 2 ln of 4 times 4 to the 2x, and here this piece right here is going to end up being 1, so I'm just left with 5e to the x. And over here this also equals 1, but I can bring that 7 out in front, so I'm left with 7e to the 7x. And this is going to be my answer. Again, I hope this helped, and remember, check back to ISO Math with all your math needs, and hope to see you soon.